So today we will talk about adversarial machine learning. So it's really like a new and a very exciting topic. And that's something which has been very, very active in the past few years. But it still remains a lot of stuff to do, and it's also a very important practical, with a lot of very important practical applications. Okay. And so what are we exactly talking about when we are talking about adversarial machine learning? Is that if you look at human vision, you will have some examples, some tasks which will be difficult for human. If you look at these pictures, for example, and you want to distinguish between a dog and a mop, for a human, it will not always be easy. Okay, so for example, when you look, I don't know, between that one or that one, is not clear which one is a dog or which one is a mop. So you have some tasks which are difficult for a human. And so then what you could have thought, is that also a neural network will also be tricked in some tasks like this. But now if you are training a neural network or some, computer vision data set, and then you try to distinguish between a dog and a mop using your neural network, you could think that your neural network will have the same problem as a human. And in fact, that is not the case. Such tasks for the neural network will be really easy. Okay. So it will be an easy task. And that's the same for a lot of other pattern recognition problems, for speech processing or for other tasks like this. So in fact, for such tasks, nowadays neural networks are even more performant than a human. If you look at the classification error at the end, neural network will achieve better performance than a human. Okay, but still, in fact, neural network will have a lot of problems in the way they are doing prediction and the way they are doing decision, in the fact that they are non-robust. Okay, so this is what we will see. And this will be really important, and even more important when we come to the time where we want to use neural network in order to make some decision. So today we will use a lot the example of self-driving car. If you want to use a neural network in order to understand the world and then to take some decision, you really want to have an architecture which will be robust, okay, and that you can trust. So we will see today that it is a major issue, and that in fact neural network can easily be tricked. So what do we mean by that? That's what we call adversarial examples. Okay. So what is an adversarial example? That's really some small perturbation that you will be able to add to a picture, and then your neural network will be totally lost. So for example, if you look at this example, I have this picture of a pig. You all recognize a pig in these pictures. And what I'm telling you is that it is possible to manually craft some small noise. So this is not a random noise. This is very important to have this in mind. This will be particularly craft perturbation. But you see that this perturbation is very small. I'm multiplying this perturbation by a very small numbers. So when I look at the resulting image, at the resulting pictures, which is exactly equal to my pig plus this small perturbation, for all of you in the classroom, you still see a pig. And you are very confident that this is a pig. Okay. But now if you ask your neural network to classify this picture, it will tell you that it is an airliner. Okay. But if you have asked your neural network to classify this picture, it is telling you that it is a pig. So you see? So for the human, it's exactly the same picture. But for the neural network, you say one is a pig and the other is an airliner. And there is nothing specific to this picture in general. What we will see today is that for any picture, it will be possible to find such perturbation so that the neural network, your neural network, will be tricked. So that's what is called an adversarial example. Okay. So you see that, contrary to human, neural network really have some difficulties with such example. And it's not hard to imagine that this will be of huge problem in terms of security. Because if it's so easy to trick your neural network, how can you rely on your architecture in order to make really important decisions? You know? And that's not only for self-driving car. I mean, you can imagine, like, if you want to use AI to do some trial, or I mean, to you know, in a lot of application, if the decisions are so less robust, how can you rely on them? So that's the first problem. And even the second problem, even if you go beyond security issue, we see that in fact we are not understanding at all how this architecture are generalizing. You know, how is it possible that in fact when I'm only changing slightly my input picture, it stops predicting well, it stops generalizing? Okay, all good for the problem we will see today? Yes. So let's try to formalize it a little bit more. So we will consider a classification problem. And we will consider a binary classification problem. Okay? So as usual, X, Y will follow some distribution D you don't know, and Y will belong to two classes. It will be -1 and 1. That's, you know, what we are used to. And typically today we will talk about neural networks. So my function F will be the prediction, the classifier learned with a neural network. But the problem of robustness really go beyond neural network. And if you consider linear classifier, you will have the same issue. Okay, so that's really something very general, which go beyond neural network. So we have some samples from D, and we are learning our classifier F. And so what we have did during all the first part of the course with Martin and with me is that we saw that in order to see if your classifier was a good classifier, you want that this classifier get a small true risk. You remember, we are looking at our classification loss, which is an indicator function of f of x different than y. So if you are doing a good classification, you are not suffering any loss. But if you are doing a wrong classification, then you will pay a price of 1. And you are taking the average of your loss over your distribution, over all your examples possible, x and y. And you remember that this expectation is exactly the same as the probability of making a mistake. So what you want in supervised, classical supervised learning is to minimize the probability of making a mistake. And you see that this is really like an average. Okay. So what we want is that when we are taking the average over all possible x, we want to find a method which achieves a low risk. That's what we have seen, and we have seen last time that neural network will work very well for this kind of task. But do you see what is the problem with this definition of the risk? In fact, why it is not satisfying to minimize such risk if you want to make robust prediction? Someone? Yes? It's not telling you how wrong you are, just that you're wrong. That could be one option, but not exactly this. Something else? Someone else? So you see that it is an expectation. So that's really like an average risk. You want that in average, you are not too bad. But it is not taking into account the worst case. So this is why what we will introduce today, it is what is so-called the adversarial risk. So what will be the adversarial risk? It will be still the average of your 0-1 loss, but not over your data x, but some small worst case perturbation of x. So you can look at the definition, R epsilon of f, your adversarial risk of level epsilon will be still the expectation over x and y following d, but you are not anymore averaging your indicator function of f of x different from y. You are averaging the worst case indicator, so you are taking the maximum of the indicator over all the x hat, which are in your ball around x. Okay? So what are we doing here? What we are doing is that we are considering that we have some adversary, and that your adversary is allowed to manipulate your input slightly. So the adversary is allowed not to tell you, no, you don't want to evaluate it in X, but you will evaluate it in X hat. And you still want to be good against this adversary. So you want to be good not only on X, but to be good on all the ball around X. And so you see that, of course, you have to impose some constraint because it will not be possible to be always good if you don't have any constraint. If the adversary can be very powerful and can, take X hat to be very far away from X, it would be a very difficult problem. So that's why that we're imposing some constraint, and we are imposing the fact that X hat is not too far away from X. So of course, you see that we will have to define what will be this distance and what will be this epsilon. So in words, really what we are doing is that for every X, you have an adversary which can find the worst perturbation under a constraint norm. Okay? And you want to be robust to this. So we can see this in these pictures. That was really like the classical risk. We have some point in green. There will be, for example, -1, and in blue there will be the +1. And we want to find a classifier which will classify well our training data. We just want to have all the green point on one side and all the blue point on the other side. That was the standard risk. Now what we are doing when we are considering adversarial risk, we are looking, so here it will be for the infinity norm. For every point X, you are looking at some ball around X, and you want that you are predicting the same label in this ball. And so now if I'm looking at this linear predictor, which previously was obtaining a very small standard risk, it was 0, you see now that the adversarial risk of this predictor will be less good, because you see that, for example, for that point, which is well classified if I'm looking at the standard risk, I will find a worst case instance here, which is not well classified. Okay, and that's the same for that point. All good? So you don't want the risk to be small for all your input X, but you also want to predict robustly in all your ball around X. That's really what is the definition of the adversarial risk. And what is very important to have in mind is that you directly see that it will be possible to have for some predictor a very low standard risk, but a large adversarial risk. So it's not because you are imposing to have a good standard risk that you will be robust. Is it good for this definition? Yes? So you see that's really why, I mean, what is in concern when you are considering your self-driving car is that you don't want, to be good in average. You really want to be good in worst case. So you really want that it will not exist some adversarial example which will trick you. So if you are able to minimize this adversarial risk, then you will get a classifier which will be robust. Okay. Are we good for the definition of the adversarial risk? That's really the most important object of today's lecture. Yes? That's a very good point, and we will talk about it at the end of the lecture. Other question? Yes? No. So you see, for now, I haven't specified the norm. We will talk about it very soon. No more questions? Okay, so you directly see that adversarial vulnerability will raise a lot of different questions. And so the first one is, how do you define your street model? How do you define what are the rules of the game for the adversary? So you see that that's really what you have to do. how do you define the adversary power? And so maybe the first question will be, which norm you want to set? Do you want to consider the L infinity norm, the L2 norm, the L1 norm, the L0 norm, which is not a norm? How do you want to characterize your geometry? Or do you want to define other set of perturbation? Here we only consider some balls, but it could be any set you can describe. So that's really like the first question. How should I define my threat model? So the threat model, that's really like the definition of the adversary power. Okay? That's the first point we will try to see today. The second point we have already talked a bit about was if you have a predictor, if you have a neural network F, which has a small standard risk, how bad can be the situation when you are looking at the robust risk? Okay. How large can be the robust risk? That's the second question we will try to solve today. We'll try to see. But then we have a lot of other questions. So for example, in the second slide, I show you like an adversarial example for the pig. How is it possible to compute such example? Do we have an algorithm such that for every picture as input, it will give you an adversarial example? And for such algorithm, you could have another question, which would be which access to the neural network this algorithm will need. Okay, that's also something we will talk about today. And so then another question could be, for example, is it possible to solve this issue? Is it possible to design a classifier F using a neural network which will be robust? Okay, how can we do so? Or maybe another question that we will not talk during the lecture because we won't have time, but it's explained on the lecture note. Now, if I give you a classifier F which is non-robust, is it possible to a posteriori transform this non-robust classifier in a robust one? That's also possible, and you can look at it in the lecture note. And then at the end, if we have time, we will try to see a little bit why, in fact, neural networks are so non-robust. Okay, so you see really like all these adversarial machine learning questions are very important, and we will try to answer some of them. Okay, but we won't have time to do everything. So let's first start with the first one. How can we generate adversarial example? Okay, how can we get this perturbation of my pig to trick my neural network? So what do we want to do? I'm giving you an input, okay, X and Y. So I'm giving you a picture and a label. I'm giving you a picture, and I'm telling you it is a pig. And I'm also giving you a neural network F. Okay, so your neural network is really a function from your space of pictures into -1, 1. -1, it's not a pig. 1, it's a pig. Okay. In the previous example, it was more complicated because it was a multi-class classification problem, and we have like different classes like pig, airliner, and so on. Here we are only considering binary classification, -1 and 1, but that's exactly the same problem. Okay, so I'm giving you an input, I'm giving you a model, and what is your task? What do you have to do? You want to find an input X hat, such that first X hat, okay, sorry for the typo, X hat is close to X. Okay, you want that your adversarial example is not too far away from your initial pictures, under some distance, which is specified. So you want this to be smaller than epsilon. And then you want that your model F makes a mistake on X hat. Okay? So you want to find a picture which is close to the pig, but when you ask your neural network, is it a pig or not, the neural network says, no, it's not a pig. And you see that's really important to impose this constraint, because otherwise it would be really easy. Like, if just giving another picture, of course it won't be a pig. So you want to find a X hat, which is close to X, so that the neural network make a mistake on this X hat. All good for the task? So you see that you have two different possible cases. The first one, which is the easy one, is that in fact X is already misclassified by your neural network. Your neural network is already wrong. So then you see you have nothing to do because you have already found a point which is very close to x because it is x. And your neural network is making a mistake predicting these pictures. So in the first case, we have nothing to do. So now what we will assume that x is correctly classified by your neural network. So we are assuming that f of x is equal to y, is the correct label. So what do we want? We want to find a point x at such that the neural network make a mistake. So that means that f of x at is different from y, and such that x at minus x is smaller than epsilon. So if we look at the picture, you see that what do we want? We want to find a point x at, which is in the ball of radius epsilon around x, and which is on the other side of your decision boundary than x. So here you see that x is on the side f of, of the +1. So you want to find a point in red such that f of x at would be equal to -1. So you see that the problem is exactly equivalent to find a point in this set, in the intersection of your ball of center x and of radius epsilon, and of all the points for which the neural network will predict that the label is -4y. So what can you do in order to find such x at? Imagine I'm giving you, infinity computational power. Yeah, we just, look around this set and try to find a point. But this will not be practical at all. So what else can we try to do? How can we find our x at? Yes? So what you are telling me is that you can, in some sense, restrict your search space. Yes, that can be an option, but can we do something even simpler? What have we done a lot during all the course? Each time we want to do something, yeah? We will do gradient descent. So we will try to find an optimization objective such that if you are solving this objective, you will find an adversarial example. Okay, and this objective will not be convex, but now you have seen that with neural network, we are not afraid anymore of non-convexity. Okay. So how do we do this? So in fact, you will see that trying to find an adversarial example will be exactly equivalent to maximizing this function. What is this function? This is an indicator function of f of x at different from y. Why is it equivalent? Because by definition, an adversarial example will be a point x at, which satisfies a constraint, such that f of x at is not equal to y. So if you have an adversarial example, this value will be equal to 1. And since this function is either equal to 1 or 0, maximizing it amounts to find a point x at where this function is equal to 1. So amounts to find an adversarial example. Okay, so you see that if I'm able to solve this maximization problem, I'm done. I have found my x at and I'm happy and I come back home. And so what is the main difference with this problem, between this problem and the one we saw previously in the course? You see that previously, when we were considering the classification loss, we wanted to do optimization over our function f. We wanted to find a predictor which was achieving a low classification error. Now my optimization problem is not anymore on my function f. My optimization problem is over my inputs. Okay, I'm looking for an input x at such that I will have a large classification error. So you see the second difference is that now we are doing maximization and not anymore minimization. Okay. And then you see, I don't know if you remember, but when we talk about support vector machine, we had exactly the same issue. Why this optimization problem is difficult, in addition of being non-convex or non-concave? It's first because the indicator function is a non-continuous function. Okay, it's going from 1 to 0 in a discontinuous manner. So you see that this function will not be differentiable in X. So it will be difficult to minimize or to maximize. Okay, non-continuous optimization is harder than continuous optimization. I mean, very often. Okay, so that's the first problem. Our indicator function is not continuous. And the second problem is that we are considering F a neural network. You know, we are considering that the neural network directly outputs the classes. So also the neural network, it is a classifier, and so is in value between -1 and 1. So you see that directly the function which go from X to -1, 1, the output space will be discrete, so it will be hard to differentiate too. So we have these two problems, and we already had these two problems where we are considering classification loss. So do you remember how can we solve these two problems? What can we do for the first one? Yes. So we can relax the discontinuous loss by another smooth loss. Okay. And then what can we do for the second problem? For the problem that our neural network output something between -1 and 1, and so it will not be differentiable. Yes. Exactly. So what, you remember that what we did is that our neural network is kind of like a huge black box, and at the end we will take a decision between -1 and 1. But in fact, it was exactly as when we were doing logistic regression. So let's see how we can solve these two problems. So for the first problem, instead of minimizing the indicator loss, okay, the 0, 1 loss, we will consider some other classification loss. So we will take a smooth one like this. We won't have any problem in order to take the gradient. So for example, we can take the logistic loss we already talked about. Okay, and cross entropy your colleague talked about is just like a generalization of the logistic loss to the multi-class case. So let's take the logistic loss. It is a classification loss, so it is a decreasing function. And so we will see it is important that the derivative of this classification loss will be negative. So that's the first point. And then the second point is that, and that's exactly the same as we did with the logistic regression, we will not consider the output F of the neural network, but we will consider the output G, which is just before. And let's assume that, in fact, our neural network is predicting a number. It's trying to estimate kind of like the probability that Y is equal to, that Y is equal to 1 given X. And with this probability, then the neural network is making a prediction. If G of X is larger than 1/2, I'm predicting that the label is 1. And otherwise, I'm predicting that the label is 0. Okay. I mean, I can change it to get 1 or -1. That's exactly the same. We could also have assumed that the prediction would have been made by the sign of G of X. Okay, if G of X is positive, I'm predicting +1. If G of X is negative, I'm predicting -1. That will be the same. But in the next slide, we will use the fact that the neural network can be interpreted as learning the probability. So it can be useful. So okay, so to solve the second problem, we are considering the output of the neural network before the quantization, okay, before thresholding the value. So we are considering the output of the neural network to be continuous. It can be in R, it can be in 0, 1, it can be not too important. So you see that now it will be possible to differentiate this function. It will be at value in a continuous space. So what is the main idea behind this? We are replacing this difficult problem, which was a maximum of a discontinuous function, over this problem which is simpler, which is a maximum of a smooth loss. Okay. So now I want to maximize a smooth function over some constraint set. Okay. But you still see that this problem will not necessarily be easy. I mean, this is still non-convex because your neural network G is a non-convex function. So you still have a non-convex problem. And we are maximizing this non-convex function over some constraint set. So it is still a problem for which it will not be possible to get, some convergence result. But still, we will see that in practice, it's working very, very well. So now the main question is how we will solve this smooth and constrained problem. And as you already say, we will try to use gradient-based optimization. But what are the main differences with before? First, I'm not anymore optimizing my function over my weight, over my parameter of my network. I'm maximizing my function over the input. That is the first difference. Second one, I'm maximizing my function. I'm not minimizing my function. And the third one, I'm having some constraint on my set. Okay. Do you have some questions on this? That's a very good question. So in fact, what we will see is that this is kind of like an overkill. Because if you think about it, you don't want really to maximize your loss. I don't know if you remember, for example, when we had that was my 0-1 loss. And then my classification, my logistic loss was something more like this. So I don't really want to maximize my loss. But of course, if I'm maximizing my loss, I will get an adversarial example. I just want to find a point where my loss will be larger than some value, so that I will be sure that G of X hat will be of the opposite, of the negative sign of Y. That's really what you want. You want to find a X hat such that G of X hat is of the opposite sign of Y. Okay? Or not really opposite. Oh. Let's forget about this because now I'm talking about G of X in value in -1 and 1. So it's easier for the interpretation. We're good for this? Yes? Okay, so your question is, can I transform my constraint optimization problem into an unconstrained optimization problem? So you could add an indicator function that would be exactly the same, but then your function will be non-smooth. You could add a regularization term, then your function will be smooth, but it won't be, it won't be a hard constraint. You won't be, the minimization of your penalized problem will not satisfy your constraint. So that's different formulation, and you can do both. But classically, in the literature, we are considering this problem. We really are imposing a hard constraint on the scale of our adversary. And you will see the fact that you have this constraint, is not difficult algorithmically. So it will be kind of the same. Okay. So you see that, in fact, we would just want to find a point X hat so that this loss is large enough. And when this loss will be large enough, then it will tell you that Y and G of X will be not the same label. Okay. So first, let's see how we can maximize this problem in what we call the white box case. So what is a white box case? That's the case where you know everything about your model G of X. Okay. You have access to G of X, you can differentiate G of X, you can take gradient, you know everything. That's what is called white box. So if you know everything and you know that you want to maximize this function, let's say first that we forget about the constraint. What should we do? Okay, we have relaxed the previous non-differentiable problem into a differentiable problem. So we want to compute the gradient of this function. So this is not difficult. The gradient with respect to my input of this function is exactly equal to what? The derivative of my loss evaluated in Y G of X times Y times your gradient of your neural network with respect to X. Okay, that's a simple computation. Is it clear for everyone to get this? Yes. And now we will use that our classification loss is decreasing. So I'm using that L prime is negative. Okay. So in fact, if I want to go in the direction which will maximize this function, I want to follow the positive gradient direction. Okay, I'm not anymore doing minimization, so I'm not following the negative gradient direction. I'm following the positive gradient direction. And so I want to go in the direction minus y nabla x of g. Okay. And you see the interpretation here. You know, if I'm telling you that g of x is a probability that y is equal to 1, you see that if y is equal to 1, you want to decrease this probability because you want to make a mistake. So you want to decrease g, and so you will follow the negative gradient. And this is exactly given by this. If y is equal to -1, then in order to make a mistake, you want to increase the probability that y is equal to 1. So you want to follow the gradient of g of x. So you see that in both cases, you want to go in the direction minus y gradient of g of x. Okay, it makes sense. So is it over? Do we still just have to do gradient ascent and follow this gradient? Pre-multiply by some step. Maybe I will do multiple steps. Will it give me the solution? What is the problem? Yeah.
We don't know if there is a transition inside of that epsilon ball. It will actually become the other label.
No, but first, I mean, even before this, so what you say is that maybe the solution will not have a problem. I mean, the problem will not have a solution. Before this, we have to take into account the constraint. If I'm just following and doing some positive gradient step, I would just diverge to infinity. Okay, so we have to consider the fact that I want x hat to be close to x. So this is what we will see now. How can we take into account the constraint? So since epsilon is considered to be small, okay, we want some example with a small noise, otherwise it's not so interesting. What I can do is that I can still consider the linearization, the first order approximation of my function. So I would just denote by L tilde, which is my function of x, okay, which is exactly L of y g of x. That's just like to shorten the notation. So what I want exactly is to maximize L tilde for x hat close to x, for x hat minus x in norm smaller than epsilon. And so to do so, since epsilon is small, what I say is that the maximization of this function is very close to the maximization of the linear approximation of this function. So what is a linear approximation? It is exactly equal to L tilde of x plus the first order approximation, gradient of L tilde transpose x tilde minus x. And I want to take the maximum of this over x hat. You see that the first part is totally independent of x hat. So I can take the maximum inside, and I will get L tilde of x plus maximum of this term. And then you see that I can just do a change of variable, x hat minus x. I can denote this delta. And so what I want to do is to maximize the scalar product between my gradient and delta for delta of norm smaller than epsilon. Okay. So this is what we would try to solve. We need to maximize the inner product under the norm constraint. And this is really what is called the optimal local update. Locally, if you are close to x and you want to maximize the most your function, it will be given by the solution of this problem. And what is nice is that for a lot of norm, it will be possible to get this solution in closed form. Okay? You have some questions on this? Okay, so you want to take the delta, which will make your linear term the larger possible so that you will make your function, your loss function, the largest possible. Okay, so that's really what is called steepest ascent. You want to find the direction which will maximize the most your function. Okay, you want to take the step which will extend the farthest in the direction of the gradient. All good? So what we will see now is that it is possible to solve it in closed form for several norms. And so that is what is called a one-step attack. Okay, we will just take one step of gradient ascent. So we want to maximize this linear function with this norm constraint. And let's consider first the case of the L2 norm. So in the L2 norm, my ball is given by this circle, okay, by this ball. I have my gradient. This is, you see, this vector. And I want to find the direction delta, the vector on my sphere, which will maximize the scalar product between my green arrow and my black arrow. So it should make sense to take delta to be exactly this vector. Okay, delta will be the vector along your gradient direction, but rescaled so that the norm of delta will be equal to epsilon. So you see that delta will be exactly equal to epsilon times your gradient of L tilde renormalized. Okay. So delta which will maximize this inner product is exactly the delta which is aligned with your gradient. And then you have to fix the scale of delta. And you know that the scale of delta is epsilon. So this is exactly the vector which is aligned with my gradient and whose scale is epsilon. I'm first renormalizing my gradient, and then I multiply by epsilon. So that the norm of delta is exactly epsilon. All good? Okay, so let's do a quick 15-minute break. Okay, so let's start again. So it was not too important, but you know, like before the break, we had like a small issue because here I'm telling you that f of x is equal to this indicator, whereas I was telling you that the label was -1 and 1. So, you know, just let's consider that in fact, f of x will be equal to the sine of g of x. So if g of x is positive, then you are predicting +1. If g of x is negative, you are predicting -1. And then for now, let's forget about this interpretation, which is not too important. Okay, so we are really following this direction. Okay. And so we start again with this. So we say that it was equivalent to find an adversarial example. It was equivalent to maximize this linear form under my geometric constraint. And before the break, we saw that for the L2 norm, the solution of this problem was given by G star of 2, which is exactly my gradient rescale times epsilon, because I want to make a step of size epsilon. So I'm rescaling my gradient. Okay, I want to go in the direction of the gradient. I'm rescaling my gradient to have a norm 1, and then I multiply by epsilon. Okay? And then we add compute what is exactly the gradient of L tilde. What was the gradient of L tilde? It was exactly minus y gradient of g of x times the derivative of the loss. Remember? It was this computation. But then what you see is that in fact, since I am rescaling, I just want like the direction. So the direction, which is given by the gradient of L tilde divided by the norm, is the sum of the direction given by the gradient of g divided by the norm times minus y. All good? So this is the output. So delta, which is maximizing locally your loss, is given by this direction. So then in order to compute x hat, your adversarial example, you just update your current point x, and you add to this x your delta. So this is the algorithm you are doing. You have a point x, and you are subtracting to this point x this gradient. And so you see that your x hat will be exactly on the boundary of your set. Okay, if you look at your constraint, it is exactly satisfied. X hat minus x, its norm, it's exactly equal to epsilon. Okay. So one question, what do you know? Well, I mean, what do you do now that you have compute x hat? Yes. What do you mean? Oh, what do you, no. What do you do now? Sorry. What do you want to do with x hat? So that's what your goal. You wanted to find an x hat such that your model was wrong. You have computed x hat, which is locally maximizing your loss. So now what you want to do is to check if this is an adversarial example or not. So we want to compute g of x hat and to see if g of x hat is of the opposite sign of y. Okay. If it is of the opposite sign, then you have found an adversarial example. You have found x hat, which is close to x. It has the distance epsilon of x, and the label has been flipped. Okay. So then we see that we can do exactly the same, not for the L2 geometry, but for the L infinity geometry. So you remember what is the L infinity norm? That's just like the max over all the components. So if you look at the L infinity ball, that's exactly this square. And so now what do we want to do? We want to find the delta, which is on my ball, and so that my scalar product is maximum. And so what you can see is that this will be exactly given by this delta. So in fact, the delta you will take is that one. Okay. So that delta will be the delta which will maximize your linear product, your scalar product between your gradient and delta under the constraint that the infinity norm is smaller than epsilon. And so this is what is called the fast gradient sign method. And that was on the first attack introduced by Jan Goodfellow in 2014. So you see what you are doing now. You are not exactly going in the gradient direction, but you are computing the sign of your gradient. And then you multiply by epsilon y. So you see that what is the L infinity norm of a vector with some plus and minus one? Okay. What is the L infinity norm of a vector with plus and minus one as components? It is 1. So the L infinity norm of epsilon y sign vector, it is exactly equal to epsilon. Okay, y is equal to plus or minus 1. So this is a plus or minus 1 vector multiplied by epsilon. So L infinity norm is equal to 1. Yes, do you have a question? You're not tracking on the... This is not working anymore. Okay, thanks. So you see that your update delta infinity is of L infinity norm 1. So when I am updating my x going in this opposite direction, I get an x hat, which is also at a distance 1 in the L infinity norm of x. So that's exactly the same as what we had for the L2 case. Okay. But now we are considering a different geometry. We are considering the L infinity geometry instead of the L2 geometry. And similarly, here, what you will do when you will have compute your x hat, you will check g of x hat to see if you have changed the label or not. But so you see that this is an approximation, so you are not, you are not guaranteed that this x hat or that one will work. Okay. And what you can imagine is that maybe for some large epsilon, only minimizing the linear approximation will not be enough. Okay. It will not really be a maximizer of your loss function. So what could you do in that case? Instead of doing only one step, you will do multiple steps. So this is what we'll call multiple step attack. That will be very close to the projected gradient descent algorithm. Okay. So sometimes one step is not enough. And so what you want to do is to do multiple steps. And it will be exactly the same as before. But now you are not doing large step of size exactly epsilon. You are doing some smaller step, okay? And alpha will be a step size that you will set. You are considering the rescale gradient, but in fact, this will not change so much. You could also only consider the gradient if you want. But you want still to impose that you are maximizing your function on your constraint set. So after each iteration, you are projecting back your iterate on your constraint set. Okay, so pi is your projection. And you see that for the case of the L2 geometry, the projection is given by this formula. It's really simple. If you have a vector delta which is outside of your sphere, the projection of the sphere would just be the rescale. Okay, so you are just considering delta divided by the norm of delta. Then you multiply by epsilon because this is a ball of size epsilon. And if your point delta is inside the sphere, then the projection of this point is identity. Okay, you stay at delta. So that's the definition of the Euclidean projection for the L2 ball. And you see that this is exactly gradient ascent. At each step, you follow the positive gradient direction, but you want to stay inside your constraint set. You want to stay inside your ball. So if your next iterate is going out of your constraint set, you will project it back to the sphere. And how do you project back your iterate to the sphere? You are applying the projection. Okay. So this is very close to projected gradient descent. All good for projected gradient descent in the L2 case? So you can do exactly the same with the L infinity norm. We are still following the direction given by the sign of the gradient. If you want, you are not really following the direction of the gradient, but you are following the direction of the update, which will maximize locally your linear form under your geometrical constraint. You are doing a small step, and you check at each step if you are staying inside your constraint or not. And if you are going out of your constraint, then you will project back. But now, what is the projection for the L infinity norm? Maybe a little bit more complicated. You see that if you have such delta, I will project, it will be exactly, this will be my projection. Okay. But you see that if I have such delta prime, which is in my corner, then the projection of this delta prime will be the corner of my hypercube. Okay. So this is exactly given by this formula. If the component of delta is larger than epsilon, so that means that you are in this corner, or I mean you are below this line or beyond that line, then it is equal to epsilon sign. And if you are smaller, then it is equal to identity. Okay. And so this is what is called a white box attack. Remember, because in order to do such attack, it can be multi-step or it can be one step. You need to be able to compute the derivative of your neural network G. Okay. So you need to have a perfect access to the network in order to attack it. And so in practice, in order to find an adversarial example, multi-step attack will really work better than one-step attack. And what you will often do is like something like 50 or 100 steps of gradient ascent. Okay. And this will work very, very well. And by doing this, you will find an adversarial example. So this is just like a small step to remind you like the different LP norms. Okay, you have different geometries. This is the L infinity norm, this is the L2 norm, and this is the L1 norm. And what is important to have in mind is that for this different geometry, it will induce different perturbation set. And so you will see it will also induce different adversarial examples. Okay. And so here we are comparing our original image and some adversarial examples found for different geometry. Okay, found for the L infinity geometry, the L2 geometry, or the L0 geometry. So how can we compare these different adversarial examples? So maybe first, you see that when you are imposing an L infinity constraint, you can really perturbate all the coordinates. Okay, that's because the L infinity norm, you can just put everything to epsilon or minus epsilon. It will still be the L infinity norm will still be epsilon. So you can really perturbate all the coordinates of your input X. So you see that here you should see that you have a lot of pixels whose value has been changed. If you compare to the L0 criteria, so you know that L0 is a number of non-zero elements. So if I say that I want that the L0 norm between X and X hat is small, that means that I'm only allowed to change a very few pixels. And so you see here that I am changing very, very few pixels. But in the opposite, here I can change with the L infinity norm, I can change a lot of pixels, but I cannot change the value of this pixel by a lot. Okay, I can only change them by the value epsilon, which is small. When I am considering the L0 criteria, I'm allowed only to change a few number of pixels, but the value, the scale of the change will not be important. So I can take a pixel which is black and I can transform it into a white pixel. So you see that's why you see all this white point. Such change will not be possible with the L infinity norm because the difference between a white and a black pixel will be 1 and it will be larger than epsilon. And then you see that the L2 norm is in between. You are allowed to change fewer pixels than the L infinity norm. So that's why, for example, maybe I don't know if you see, in the L infinity norm, I have all this gray space, whereas for the L2 case, I'm not changing all these pixels. But what is important to have in mind is really that the geometry you are choosing, the geometry you are imposing, is changing the kind of adversarial example you have. Okay. And so in practice, that's really very important to define what is the set of perturbation you want to be robust to. It's not clear at all. For your application, to which contamination you want to be robust. And that's very important, direction of research to be able to define what is the right perturbation set. Okay. For your application, to what do you want to be robust? Maybe you don't want, you don't care about L infinity perturbation, for example. So in practice, how do you do your white box attack? So for your neural network, it will be very simple to compute the gradient of G doing backpropagation. Okay, and in fact, it's already implemented in a lot of library, and that will be the object of the next lab. Okay, so this is not too difficult. But then you can ask the question: is it like a legit assumption to assume that you know G? Is it, do you have access to G? Can you compute the gradient of G? So that really depends on the application. For some practical application, you could imagine that yes, you can have access I don't know, for example, for a car, you can buy the car and then you can, do a lot of experiments for the car and you will have access to the neural network. And so you will be then able to attack it. But in other application, you could say that you will not have access to G. Okay, you will not know the function G. You will only have access to the prediction of the neural network. And you can still ask the question, is it still possible to find some adversarial example in that case? That's what will be called the black box attack. Okay, so white box, it's when you know the function G of the neural network. Okay, you have a description of this function and you can do some back propagation of this function. And you can compute the gradient of your neural network prediction. And then you will be possible to implement some PGD attack. Black box will be you don't have access to G. Okay, you have only access to some information. And what are this information? You have the score-based case. So the score-based case is that you have access to the model score. So you don't know the function G, but you have an oracle. If you give X, I will give you G of X. Okay? So I mean, you can't differentiate directly G because you don't know the structure of G, but you have access to the values that G will take. So this is a score-based case. And then you have another case which is even harder, which is you don't have access to the score. You only know the prediction. You only know if X is a pig or is not a pig. You only have access to plus or minus 1. And that's the case, for example, sometimes with some API. You have like something in the cloud and you can give him X and it will tell you the prediction. So you will only have access to +1 and to -1. And with this information, you will still want to be able to find an adversarial example. Is it clear for the setting, for the difference between white box and black box? Yeah. White box, you know the function G and you will be able to differentiate it and to compute the gradient. Black box, you have only access to the function taken by G, or even worse, to the prediction made by the network. Do you see that the problem is harder in that case? Is it clear or not? If you have only access to the prediction or to the score, it will be not possible to compute the gradient. Okay, so what we have defined previously, you cannot do it directly. Yes, what is your question? Why sometimes you know G or sometimes you don't know G? That's a good question. So in practice, for example, you can think that you want to attack something you have access to. Okay, so you have an experiment and you want to attack this neural network. Okay, so then you can do back propagation along this neural network, and so you will know the function G. But sometimes what you want to do, and this will be more relevant in practice, you want to attack a G you don't know. Okay, you want to attack an algorithm of some company, let's say. So here the company will not give you its network, but you will be able to query the AI of the company and to ask him, okay, can you tell me what do you have on this picture? So you see that for this kind of application, you will only have access to the score or to the predicted class of the neural network, but you will not have access to the structure of the neural network. Okay. So what can we do still to attack our network? The first solution is kind of easy, is to say, okay, I don't have access to my function G, so I cannot compute my gradient. But in fact, that's something which is well known in optimization. That is what is called zeroth order optimization. How can I minimize a function if I only have access to the function value? And so what you can do is that you can just approximate your gradient using the finite difference. Okay, you know that the gradient will be the variation of your function. And so in order to approximate the gradient, you can just compute in all the direction how your function value is changing in that direction. So you know that G of X plus alpha EI minus G of X divided by alpha for alpha small, that will approximate very well the directional derivative of your function G. And so then if you do this in all the direction, you will get a good estimate of your gradient. Is it clear for you that by doing finite difference, I can get an approximation of my gradient? Okay, the gradient is really telling you how your function is varying in the space. So if you are looking at some small difference between g of x and g of x plus alpha, a vector, this will approximate the derivative, I mean the directional derivative of g. And you just have to do this in all the direction, and then you will get an approximate of your gradient. Okay. But you see that in order to do this, it will be easier if you have access to the score g of x. If you have only access of f, it will not be as easy. So it's still possible to do so, and if you are interested, you can read about it. But this will really work well in the case when you have a score-based access to your neural network. So what can I do, in that case? How can I still attack my network without trying to approximate my gradient? So what we can use is also what is called a transfer attack. That's something which is kind of nice. So what is a transfer attack? It will be, okay, I don't know my network F. I only have access to F, but I don't know the structure of F. But then imagine that I have access to some data where my network has been trained on. Okay. And then imagine also that I have access to a model F hat, which is kind of close to F. Then maybe I will be able to train this network F hat such that F hat will be close to F. But know this network F hat, that's a network I have trained, that's a network I have access to. And so I can do a white box attack on this F hat. So you start from F, you build a surrogate of F, which is called F hat. That's a function, that's a network you know. And now you can attack this network F hat. And then what you can hope is that the attack, that the adversarial example you have found for F hat will transfer to F. So this is what is called a transfer attack. Okay. And so you see that one case where it is possible to do this is a case where it's possible for you to do a lot of query to F. If you can do a lot of query to F, then you can use an unlabeled input xi. Okay, you just take any pictures you want. You ask F, what is the label of these pictures? Then what you will get is you will get a new train set, xi and f of xi. This is a new train set that you have built using your network F. And now you will learn your F hat based on this new train set. So you see that it is called model stealing because in some sense, you will steal the model F by learning a new model so that this new model will make the same prediction as the model you are trying to steal. Okay. And now with this new model F hat, that's a model you have trained, so you have perfect knowledge of it, and you can apply white box attack on this F hat. And so, of course, you see that the success of this transfer attack, the fact to see if an attack of F hat will transfer to F, will depend a lot on how similar the data you have used were to the initial data you are, on which were trained F, and also how similar were the architecture of F hat and F. So of course, in practice, for a lot of application, you will only have access to the prediction of F, and you would not know, what kind of neural network F is. So it will be not, it won't be obvious to find which architecture to train. And also, you can see that in practice, if you are asking, to the company or to the API a lot of label in order to build your new data set, it will easily detect you and easily block you. But in fact, this still works well if you are not, for moderate size of a new train set. Okay, so this is what is called the transfer attack, and you see that we can use this transfer attack to do some black box attack to a neural network. So to conclude about black box attack, in practice, I really have practical concern, but still, in fact, query-based methods, which use a gradient approximation, they require a lot of query in order to find an adversarial example. So I don't know if you remember, but previously I told you that when you were doing white box attack and you were doing PGD, if you were doing 50 or 100 iteration, it was enough in order to find an adversarial example. If now I want to use a black box attack, I will have to do of order 10K or 100K in order to find an adversarial example. So you see that we will have to do a lot of queries to the model in order to find an adversarial example. And so it would be really easy to restrict the access to the attackers. You know, if you are asking to an API this amount of query, it will easily detect you and block you. And that's the same with the transfer attack. In order to find the surrogate F hat, it will often be very costly. You will have to do a lot of query. The success will not be guaranteed. And also it will be kind of hard to find the good architecture to train. So you see that in all this, we are still kind of far away to really physically reusable attacks. Some really attacks that you can deploy on the wide. This is what we will briefly talk about now. You know, like you want to find an attack that you will be able to realize in the real world. And in fact, in order, you know, to apply in practice your adversarial example, you will have to satisfy some further requirement. So in some sense, you should really survive to some post-processing operation that will differ following the different application. So for example, often when you will build adversarial example, then you will compress the pictures, okay, using like a JPEG compression. And then when you will compress the picture, it will change the picture, and the JPEG compression of your adversarial example often will not anymore be an adversarial example. So you have to try to take this into account. Another example is that this example of the stop sign. Okay, so what you want is to be able to attack a self-driving car. So what you could do is that you can directly attack the car, but that can be difficult, you know, to change the software of the car. So what you can decide to do is to, in fact, attack the real world and try to modify directly the stop sign. So what you are trying to find is a way to put some patch on your stop sign, to modify the real, you know, reality of the physical signal, so that now the camera in your car, when it will be look at the sign, it will not anymore see a sign, I mean a stop sign, but maybe it would see another sign. So your car will not stop. But you see that now this problem is really more difficult, because previously I had like some fixed problem. I gave you an X and a Y, and I wanted to find an adversarial example. But now you can imagine that this stop sign in the reality will correspond a lot of different pictures possible, okay? Because your car can be in a lot of different positions. So you have to be able to find some adversarial example which will work under, I mean, the invariance over all the camera angles, the distance, the weather, and so on. So that's something which is really very trendy, and if you are interested, you have a lot of paper about this. But in practice, it is working quite well, okay? So for example, with these patches on the stop sign, this will work. So on the other hand, you could say that this is not anymore really like an adversarial example, because these signs are noticeable by the human, okay? So in some sense, it's kind of easily detectable. But still, for you, it's still easy to detect this stop sign as a stop sign, but your automatic car will still think that it is another sign, and it will not stop. Okay. So we have talked a lot about different attacks: white box, black box, and then other one. What we will talk about for the last 15 minutes is how is it possible to train some robust model. You know, what is the solution to this robustness issue in a neural network? So this is what will be called adversarial training. Okay, so we want to fix the robustness issue, and we want to find a way to train some model which will be robust. So what do we mean by robust? We mean that it will not be possible to attack this model. It will not be possible to find adversarial example which will trick your new robust model. So this is what is called adversarial training. So let me remind you that what we have did previously, when you had like a training set, you know, you wanted to find some model with a low training error, and so that was the standard training. So the goal of the standard training was to minimize the standard risk. We wanted to find an architecture, f theta, okay, where theta is the parameter of your neural network, the bias, and the weight, such that the standard risk, which is the expectation of your 0-1 loss, is small. And what we saw is that minimizing the standard risk is not enough in order to get some robust model. If you have a predictor, a neural network with a good standard risk, it will still be possible to attack it by doing some white box attack on it, and it will not be robust. So instead, if you want to find a model which will be robust to attack, what we will have to do is to minimize the adversarial risk that we have defined at the beginning of the lecture. So the adversarial risk, let me remind you, is the same as the standard risk, but I'm not anymore looking at the 0-1 loss evaluated in X. Okay, there is no at here. But I'm looking at the 0-1 loss evaluated in for the worst point in my small epsilon ball. Okay, so I want to minimize this worst case risk. If I'm minimizing this worst case risk, then it will be not possible to find an adversarial example. Okay, because it will not exist some point x hat such that I will have a different label in my ball. Okay, so we want to do this. So how we will do that? As previously, we have two main problems. The first problem is that we don't know the distribution D. That's the problem we had since the beginning of the course. So how we will solve this, we will approximate our true expectation by the sample average. Okay, so we will consider our training loss, the average over our training data. And the second problem, we already talked about it today, is that our indicator loss is non-continuous. And so what we will do, as in the SVM course, we will use some surrogate for this indicator loss, and I will consider another loss, the smooth loss, for example, the logistic loss. And so you see that this will amount to minimize the following problem. I want to minimize over the parameter of my network my training error, and so my average worst case loss. For all my data set, all my point xi, I want to find the worst x tilde I in my ball, and I want that my loss is small for this x tilde I yi. Okay? It should be clear that if you find a theta which will minimize this objective, then you will get some architecture which will obtain, which will be robust. So you see that this is called min-max problem. Okay, you have a problem, you want to compute the mean for theta over the max for all the xi tilde. Okay. So how will we maximize, how will we minimize this function over theta? What do you think? Yes?
Show that it's convex, like, or take the derivative
So do you think it will be convex? Okay, it won't be convex because I have a neural network in it. We will do gradient descent, but I have to deal the fact that I have this max. So you could switch the max and the mean. So in fact, it will be difficult to switch the max and the mean because you see that this mean is independent of theta, whereas the max is over xi. So you can think about it is not obvious. And anyway, this will not, I mean, you are not guaranteed that the min max will be equal to the max. So instead, what you will do is that you will approximate this max using your adversarial example. Okay. So in order to minimize your average loss of your average worst case loss, what you will do in adversarial training is that at each step first, you will compute some adversarial example. So you will compute some x tilde I, which approximate this problem. Okay. So using the PGD attack, you will find adversarial example for your model at the step t. Okay. Should be theta t. So at the step theta t, I mean at the step t, you have your model with your weight and your bias term theta t. Okay, you have a model, and what you will try to do is to find for all your observation some adversarial example for this model using your PGD attack. Okay, and then using this x tilde I, you will approximate the sum of this maximum of the loss by the sum of the loss evaluated in your adversarial example. Okay. And then you want to take the gradient, so you will get exactly this. Your gradient step will be the average of the gradient of the loss. So this is exactly what you will have done if you would have used vanilla gradient descent to train your neural network. But you see the difference that now you are not evaluating your loss in your observation xi, but you are evaluating your loss in your adversarial example x tilde I, okay, that you have computed at each step. So you have this algorithm. At each step, I start with theta t. With this theta t, I have my model G of theta t. I will attack for all my observation. So I will compute adversarial example x tilde I. And then I will use these adversarial examples in order to update my parameter theta t. So theta t plus 1 will be equal to theta t minus some step size times the gradient, where the gradient is evaluated in my adversarial example. Yes, you have a question?
But trying to minimize the adversarial risk, we are increasing the standard risk. So maybe we can incur some misclassification, and so we can recognize the stop sign as a limit to size, and we have the same problem.
So yeah, that's a good point, and we will talk about it next time. Okay. So is it clear for the algorithm? You see that's really close to standard training, but instead of computing your gradient in your observation xi, you are computing your gradient in your adversarial example x tilde I that you have compute using the PGD attack. So you have kind of like a two-step algorithm. With theta t, you will compute all your x tilde I, and you will use all this x tilde I, all your adversarial example, in order to update your parameter. Is it good for the definition of the method? Okay, so in practice, the good news is that it is working very well. And if you want to find a robust method for classification, really adversarial training is giving you state-of-the-art results. So that's a method which in practice works the best. Another positive side, it has, in fact, also in practice, it will give you some more interpretable gradients. So this is what we can look at this. If I'm comparing, for example, some standard model, so that model which have been trained using standard training methods, and some method which have been trained using some robust method. And I'm looking now at the gradient of my loss with respect to the input. You see that the output will be more interpretable for robust model. Okay, you see that the gradient of the loss, it's closer here. I mean, it's only activate where the picture are active. Whereas when you are looking at the gradient of the loss with respect to the input for standard model, the signal is meaningless. And also what is very nice with this algorithm of adversarial training is that it is fully compatible with HGD and mini-batch SGD. And so it will be possible to implement it easily. And this will be also the object of the lab 10. So then what are the bad news? And that's what was your question about, is that first at each step of adversarial training algorithm, you will have to compute all this adversarial example. Okay? So for each step, for all I, you will have to do some step of PGD. And if I told you that in order to find an adversarial example in practice, you were doing 50 to 100 steps of PGD, when you want to train a network, you can do less. Okay, you can only do maybe 10 steps of PGD. But still, you see that you will have an overhead. It will take you 10 times, 10 times more time to compute and to train your network with adversarial training. So that's the first bad news. And the second one is that you have this trade-off between robustness and accuracy. This means that by training your model with robust training, you will get an architecture which will be more robust, but it will be also less accurate if you are just if you are just interested in average case performance. Okay, there is no win-win. If you want to become more robust, then you will have to be less efficient in the average case. And so this is what you can see in these experiments. Okay, you see that the standard accuracy, when I'm considering some robust model for this value of epsilon, is going down. Okay, so if you are comparing of a robust, of a clean model of a vanilla train model in black, a model in blue for a small value of epsilon, and then you increase the value of epsilon, then you see that your standard accuracy is going down. So by improving your robustness, you will decrease your standard accuracy. And so this is what is called really like the robustness accuracy trade-off. So you have to pay the price, and this is a trade-off, and you have to decide, how much you are willing to lose in terms of standard accuracy in order to win a bit of robustness. So that will be all for today. In the lecture note, you have this very nice example which kind of explain, why adversarial example exists and why is it possible to get some very large robust error, but still very low clean error. So you can have a look at it. Okay, thanks and have a good evening. Bye-bye.